Okay, so thanks everybody for joining us here for this talk, for talking about machine learning integrity to the quest to awaken the true force of AI. So my name is Yaron Singer. I'm co-founder and CEO here at Robust Intelligence. Excited to to tell you about machine learning integrity. So I think it's no secret that AI is eating the world, and one of the ways that we can kind of present that is by basically looking at how much AI software are people buying around the world. And what we're seeing that there's this massive increase in the adoption of AI by looking at just how much AI software is being sold. But at the same time that we know that AI is eating the world, we know that AI fails all the time, right? So we know that AI models fail sometimes because of corner case inputs. We know that AI models fail because of biased predictions when basically we're training AI models on one type of data, but then using them on another kind of data. We know that AI models fail because of unexpected model output when sometimes these models go haywire in unexpected ways. We know that AI models fail when there's shift in the data distribution, right? When we train models on one kind of distribution, but now we're experiencing something else. We know that AI models fail because of adversarial inputs, meaning that we have adversaries that are actively manipulating data in order to fool these models. And then we know that AI models fail because of broken data pipelines. So all these are just different reasons for why AI models fail. And when I say that AI models fail, really what I mean that input is coming into these models, so data points are coming into these models, and predictions are being produced by these models, but these predictions are wrong. So really when organizations are adopting AI, they are adopting AI risk. And we call AI risk the set of operational challenges that are exposed by AI systems that are just not present in traditional software systems. And all the causes that we talked about distributional drift and unexpected model output, broken data pipelines, bias predictions, corner case outputs, and adversarial inputs, they're really just all kind of like these symptoms of AI risk. So if we think about the pain of organizations that are adopting AI, really what we're saying is that pain shifts towards risk. And a good way to sort of think about this is to think about where were our biggest pain points back in 2015, right? Not that long ago. So in 2015, this is basically the time that predates TensorFlow, predates PyTorch, it predates even scikit-learn, right? So basically, back in 2015, if you wanted to deploy AI models in production, right? AI development was your first and biggest hurdle towards that goal, right? And then that's kind of like where you'd spend most of your efforts. Fast forward to like 2022, we have a lot of automated ways of basically creating models, right? So developing AI models is not the biggest factor. That's not the biggest obstacle, right? Right now, one of the biggest obstacles is deploying these models in production, right? And that's where a lot of effort goes into. But now what we're also seeing that as these models go into production, AI risk and the issues that involve AI risk, that becomes a huge issue. And when we think about where we're going to be as a community 3 years from now, right? AI deployment is roughly going to be solved, right? In that, we'll have better practices and be more knowledgeable about how to execute AI deployment, right? But AI risk is a problem that's here to stay. And that's where we're going to be spending the majority of our efforts on, kind of like similar to, if we think about the relationship between the networking community and the cybersecurity community, we know how to deploy networking protocols and we know how to have fast internet, but we're still dealing with kind of the consequences of risk, in network environments. So our mission really is to eliminate AI risk. And a different way of, presenting this as a mission is to deliver end-to-end machine learning integrity. So my main statement here, and if you sort of think about like the 3 takeaways they should have from this talk, I hope these can be your 3 takeaways. So the main takeaways are that end-to-end machine learning integrity is achieved by testing. So specifically, the first point that I want to make is that model failures due to bias, bad input, drift, adversaries, they're really all symptoms of AI risk. And what I mean by that is I mean that they're not disparate problems, that we need to think about them separately, or that we need to think about different processes for each one of them, but we really need to think about all of them under one umbrella of AI risk. The second bullet point that I want to make is that every one of these AI risk symptoms can be mitigated through an appropriately designed test, right? And again, what I mean by that is, I mean that we can build and create tests so that these tests are able to, mitigate the effects of bias or bad input or drift or adversaries, right, on our AI models. And then finally, the last point that I want to, that I want you guys to keep with you is that testing is a powerful framework for preventing and monitoring AI risk symptoms, so that we can, and basically we can use that system to enable end-to-end machine learning integrity. And really, that's kind of the main point that I'm going to try to convince you throughout the rest of the talk is about, testing being a powerful framework that is appropriate for ML integrity. So the first thing I want to talk about is I want to talk a little bit about what are some of the technical challenges that stand in our way for achieving machine learning integrity. The second point, I'll talk about, what is a testing-driven approach to achieving machine learning integrity. And then I'll talk, I'll give a few examples and case studies, and I'll conclude with some, some brief takeaways. So when we think about what are the technical challenges to ML integrity, the first thing we need to look at is we need to look at the ML or the machine learning lifecycle. So we know that, developing, ML models in production, right, requires a good amount of data engineering. And then once we do data engineering, we move into the stage of model building. And once we're done with the model building stage, we go into model optimization. And really every one of these, data engineering, model building, and model ops, right? They all have kind of like separate components and processes that go in there as well. So in data engineering, we have processes around, data cleaning, data exploration, and feature engineering. And in all those, we're facing with various technical challenges. So in all these, in this data engineering process, we're facing with broken upstream pipelines, outliers, we're facing data leakage, features, issues with like feature selection and scaling feature selection, and then oversampling. So these are all technical challenges that we as data scientists face, right, when we're performing data engineering. The second piece is once we're through with data engineering, we go into the model building component. And in the model building part, that requires training models, evaluating models, doing tuning and hyper tuning, and then also retraining models right after they go stale. And in this part, we're also facing with myriads of issues and technical challenges, all that go into performance on performance of models on edge cases, dealing with underperforming subsets, dealing with bias against protected attributes, vulnerabilities of our models to various data corruptions, vulnerabilities to evasion and adversarial attacks, and then really kind of like being able to create a standardized heuristic that serves as like, decision, and basically having like decision processes, right, that tell us like what is the best model or model architecture that we should apply, for our business problem. Finally, when we're actually deploying the model in production, then we see various issues there, all the way from the actual deployment, working with IT on that, to like dealing with model serving, model monitoring, and model selection. These are all issues that we're facing when we're doing the model ops. And here, again, we're seeing kind of issues with ensuring reproducibility of feature computation pipelines, ensuring data is free of corruptions, ensuring that we basically have a consistent schema. We need to deal with degradation of model performance. We need to know how to estimate performance in the absence of labels, right? And we basically need to figure out, like in many cases, how do we automate the retraining pipeline? So really, like all these technical challenges that we've enumerated here, they all kind of translate back into risk, right? So all these technical challenges around data engineering, model building, model ops, they all translate to risk around model performance, fairness, security, and transparency. And when we're talking about machine learning integrity, really what we're talking about is we're talking about the set of practices to eliminate these kinds of risks through the machine learning lifecycle, right? So how do we eliminate these technical, all these kind of like technical problems and challenges, right? So that we devoid ourselves of machine learning or AI risk. So to get us kind of like, more into kind of like the technical details, I want us to like talk about, a testing-driven approach to achieving machine learning integrity, which is the approach that we take on here at Robust Intelligence. So maybe like before we talk about the, what is a testing-driven approach, it's going to be valuable to talk about what is not a testing-driven approach. So something that is in contrast to a testing-driven approach is a BI approach, right? Or business intelligence or business analytics approach, right? So roughly speaking, a BI approach means that what we're doing is we're tracking customized metrics using dashboards, right? And this is this is a practice that we've inherited from business analysts, right? Which basically says that what we're doing is we're creating customized metrics, right, in KPIs, and then we're tracking them by using dashboards. So when it comes to the machine learning pipeline, really what it looks like is we perform data engineering, and after we kind of create do data engineering, we go through the model building component, and then once we have models that are serving in production, what we then do is we monitor the, we monitor kind of performance metrics of these models, right? And then we basically we view these performance metrics in dashboards. So that's the business intelligence approach that we inherited, right? That makes a lot of sense in for business analytics, right? And this kind of approach is it has a lot of advantages, and some of the advantages are that it's really easy to set up, right? Specifically, right, it doesn't require any context about the data, the model, right? And it really requires no understanding of machine learning, right? So really anybody can set up thresholds, right? And basically track these thresholds and monitor them and see kind of and see their performance over time. Moreover, right, except for the fact that that they don't require like any understanding of machine learning, right? There are really great open source visualization tools and and databases that we can use, like kind of like Grafana and Prometheus databases that make it like really easy to create customized dashboards, right? And in that sense, this is a very natural progression for an individual data scientist, right? So once we graduate from notebooks, it becomes very easy to set up basic kind of like using kind of like basic open source BI tools, right? So we can now track the maybe like prediction performance of these models, right? When it comes to machine learning integrity, though, a BI approach is something that is not ideal. Probably the first point that that is important to make here is that a BI approach is focused on reporting on failures, but doesn't do much to prevent failures, right? So if we're kind of thinking about this as if we're tracking predictions and we're basically using a BI approach, we would be kind of like notified when after predictions fail, but we're not doing anything to like actively prevent these failures, right? So this is akin to kind of like knowing that your house was on fire last week, right? Versus actually doing something to prevent that fire. Other points are that basically it's very difficult for an organization to standardize quality, right? And the reason is because if we're leaving it up to individuals to kind of like set up their own metrics, setting up their own thresholds, right? It basically gives a lot of flexibility And at the same time, it's like really difficult to standardize like kind of, the quality control, right, across an organization, right? And then finally, like the fact that, with a BI approach, we require humans to set up and interpret, the results, it means that it's very difficult to scale. So if you have like tens of models, let alone like hundreds of models, right, it's going to be very difficult to set up a customized metric, right, for every one of these models, right, and to set up customized thresholds, right, that are informative, right, for every one of, these tens or hundreds of models, right, and then being able to kind of like track that, in a meaningful way. So when we're looking at, not in business analytics, but we're looking at what does software engineering and cybersecurity do, really, they rely on a testing-driven approach. And that's the approach that we're adopting here at Robust Intelligence. So a testing-driven approach is fairly, conceptually, it's very simple. What we're doing is we're basically running, we're automating tests so that we can run, hundreds of tests on the test for various symptoms of AI risk, right? That can either pass or fail based on the, severity metrics that are tied to the impact that these issues have on models. So basically, we can test different attributes of data. We can test different attributes of the model, right? And then these tests can either pass or fail based off of the effects that the different issues have on the model. So to be a little bit more concrete, if we're thinking about the ML development pipeline, we're thinking we're starting from data engineering, right? And the first test that we would do for data engineering is we run a series of data tests. And after running a series of data tests, some of them pass, some of them don't pass. And we can be informed with about passing or not passing with different levels of severity. So if I think of an example where one of the tests that we can run here is we can run basically a test to test for unseen categoricals. Are there features that have categories that haven't been used in the training data, right, that are observed in production data? So we can do testing for that. And then when we do testing for that, the test can come back with either pass or fail, where fail would, in this case, would mean that there actually are unseen categoricals, right? And then we can measure the effects of these unseen categoricals on the actual on the performance of the model. The second part is when we're doing the actual model building. So this is where what we would do is we would basically stress test the model. So we would run a series of tests that that look for various sensitivities, vulnerabilities, attributes of the model, right? And then we would dump these tests into results that we can then read. So if we think about unseen categoricals, right, in the context of model building, unseen categoricals, we would then test how a model responds to an unseen categorical. So we would introduce unseen categoricals, and we would and then we would run these these data points with unseen categoricals on the actual models, right? And then we would see whether that affects the performance of the model, right? And then we would get the result. In this case, we can also view this as a with the UI, right? And we can see the sensitivity of a model into, in this case, single feature changes. And then finally, now that we're done with the pre-deployment aspect of it, now when we're actually thinking of taking a model and putting it in production, the first part of what we can do with testing is we can basically compile the results of these tests, right, into what we call an AI firewall. So an AI firewall would basically be a set of tests that we're running, that we're basically using to wrap the model around. So we can then in real time test for various attributes of the data, right? And we can then flag or block bad data points if they're going to harm or the model or produce bad predictions, right? So when we run it in real time, we can actually get real time reporting on data points that are failing, and then we can also dig into these data points and see why they're failing, right? And these are basically the tests that they're failing on, right? So this is what a view like that would look like. We can see a data point. We can see that it's passing on certain tests or certain features, but then there's one feature that that's being flagged, or one test that is being flagged on, where it's there's a problematic issue. And then, so this is when the models are actually running in production. But in post-production, what we then do is we can take the data logs, and then from the data logs, we can actually run continuous testing. So we can just continuously test. We can just continuously, run tests on the from the prediction logs, and sort of see what sort of tests are passing, not passing, and view patterns over time in the data, right? And then, as we're running these tests, again, we can sort of see various trends, and we can attribute these various trends into tests that are passing or not passing, and then we can dig into those and see what are the actual issues, right? So basically, by going all the way from a single test, we can then run chain kind of tests into a complete system that gives us end-to-end machine learning integrity, all the way from data engineering through model building to model ops, from real-time prevention of errors, right, to continuous testing, preventing errors post-production. So just quickly mentioning some case studies, right? With Expedia, we're looking at a big organization that is running robust intelligence plus Databricks to eliminate AI risk. Expedia uses hundreds of models, right? For various predictive tasks, and roughly and quickly scaling up the machine learning organization, right? So we have the biggest challenges there are basically to ensure that models are running reliably at scale. Data scientists are saving time, not wasting effort on firefighting various issues. And then basically we have multiple teams across the globe that are developing and deploying numerous models, right? And all this requires a very standardized approach to evaluating and testing models in production, right? And then of course, model errors introduce risks to various organizations, right? And can hurt end users and business KPIs. So basically, by using kind of end-to-end testing, can basically have Expedia using this for experimentation and monitoring, building in kind of integrations throughout ML development cycles, usage for NLP and tabular support, and getting basically integrated results with business dashboards. So from the deployment pipeline, here looks something like this. This is a very heavy Databricks shop, right? So all the way from in the data preparation phase, you can connect to Databricks and PyTorch and MLflow. All this is run on stress testing. So robust intelligence connects to all these aspects with using AI stress testing for data and model, right? The results of stress testing are then compiled into an AI firewall that gets used for real-time models, and then afterwards those are processed and then we run continuous testing. Similar case study is a customer in the HR and payroll tech world, right? That is using this is again a very big organization, hundreds of thousands of customers, leading basically with a very strong 25 machine learning teams again across the globe, right? Using machine learning models to make predictive analytics around payroll and HR. Main challenges, is a lot of it is around bias and fighting against bias. So there's New York City law that introduced there's a new law that requires organizations that are using automated decision-making processes to do regular audits. There's an EEOC that's introducing guidelines on regular testing and continuous testing against potential bias and discrimination in HR-driven systems, right? And now, again, we have multiple teams across the globe, deploying numerous models, and we want a standardized approach, right, that makes sure that we're not introducing any risks, right, using AI. So here there's a lot of focus on compliance-based testing suites, auditable pipelines, surfacing kind of like the most important issues, rich APIs for integration, and reporting through model scorecards. The data pipeline here looks similar, where again, heavy Databricks shop, where we're using stress testing for kind of like the components of data preparation to model building and model registries, right? Using AI Firewall for real-time model protection and continuous testing with batch analysis to continuously test models. So the main takeaways are one of the biggest pains of production in ML is AI risk. We see model failures due to bias, bad input, drift, and adversaries. They're all really symptoms of AI risk. And what we advocate for is the testing-driven approach that can provide an end-to-end machine learning integrity by testing, preventing, and monitoring symptoms of AI risk. So with that, I want to thank everyone for attending the talk, and hope to take questions here and offline. Thank you.